All right, hello everyone. So I'm going to present this paper, exF2FS, transaction support in log-structured file system. It's from this year's FAST from the OS lab at KAIST. So just to briefly go over the transaction basics again, we have four properties: atomicity, consistency, isolation, and durability, and we call these the ACID properties. Don't need to follow every single property if we don't want to. For example, some databases or file systems just choose atomicity and some others. So it's implementation dependent which ones we want. So for atomicity, we can say either all of a transaction completes or none of it completes. So we have a transaction here on the left where we write A, B, and C, but for some reason, the write to C fails. And when this transaction finishes or cancels or rolls back, we don't want to see the updates to A and B in the database. We want everything to be as it was before the transaction began, and we call this atomicity. For consistency, we can say very broadly that transactions don't violate integrity rules on the database. Kind of hard to get a solid definition for consistency, but for example, we don't want to update rows that don't exist. And another example might be that when we want to update something in a transaction, there might be some rules. For example, customer balance can't be negative or something like that. And the various definitions of this seem to exist, and it seems to change everywhere you look. Isolation, we can say, for one definition of isolation, we can say that transactions don't want to see the changes in progress in other transactions. But this one again varies between the applications. So some applications you can choose to see ongoing changes in other transactions, and then you can choose not to. So in this example here, we have two transactions updating the same stuff, but in the level of isolation we just talked about, we don't want them to see the changes from the other transaction. So we say the transactions are isolated. And finally, we have durabilities. So when we make a change through a transaction and it returns successfully and commits, if the power fails or the system crashes or something, we want to see those changes after we restart. But what can happen is things can become very difficult if the file system itself doesn't support transactions, which actually seems to be the common case. So as an example here, we have what a transaction looks like in SQLite across multiple databases or multiple files. And we can call this just a multiple file transaction. And because we don't support transactions or some sort of transaction primitive in the file system, in this example, what we need to do is create these journal files and this master journal file to record, which journal files were updated. And keeping these journal files consistent and persistent involves a lot of fsyncs, at least in this example, which, as we'll see later, can significantly sort of increase write amplification and the time it takes just for a transaction in general. So in this example, or the example they give in the paper, we have this SQLite transaction that updates 3 files. And if we want to write just 3 100-byte updates to the different files, in total, we have 15 fsyncs and 180 kilobytes written just for 3 updates, 300 bytes. And the reason is because the file system isn't supported action, we have to rely on these rollback journals and master journals and implement transactions at the application level. And we can say that, at least in this scenario, because the file system didn't support some sort of multi-file transaction primitive, this is the reason we had to do all this complicated work just to support a simple transaction. But there are a few challenges in multi-file transaction support, at least at the file system level. So one thing is that what if we want to have a transaction across a lot of files, but the total size is very large? And because in general, the updates in the transactions are going to be kept in memory, but current file systems that support transactions, or at least research file systems, the support is quite poor for such a use case. So in the ext4 based ones, as they describe in the paper, there's sort of a limit on the size of the transaction related to the size of the journal. And even transactions can maybe go across one journal to another after the journal is synced or something like that, further increase. And then if we look at exF2FS, which kind of supports a very primitive transaction, it just supports atomic writes. If there's too much memory in use for the transactions, it just aborts all transactions. So support is very poor for such a use case. And another problem is that in a file system with garbage collection, what would happen if the garbage collection started while a transaction was active? And what could happen is that pages that aren't included in the transaction are targeted for garbage collection, causing all sorts of consistency or integrity issues. As an example in exF2FS, if we have a transaction running some atomic write transaction and garbage collection tries to claim one of the blocks, it just cancels the transaction. So the support is generally quite poor. And because of these challenges, it requires sort of fundamental overhaul of how the transactions work at the file system level. So in this paper, they introduce exF2FS, which is an extension of f2fs. And what they provide is this API that allows us to have multi-file transactions, but at the same time allows us to swap pages to the disk without breaking the properties of the transaction. So it allows us to have these large ongoing transactions, and at the same time puts the framework in place that so we can garbage collect while a transaction is running without breaking the transaction too. So to do this, they add three things to f2fs, and they add them carefully enough that an exF2FS system can just mount the previous f2fs with no problems. So the first one is membership-oriented transactions. The next is page stealing, and then the next concept is called shadow garbage collection. So for the membership-oriented transactions, on the left here, on the top, we have a transaction, the same ones before, write file A, B, and C. And on the left, how it looks like in f2fs is that when we modify the page of something, the dirty pages are stored per inode. So fundamentally, we can't support a multi-file transaction because it's just per file, at least in the current version of f2fs. So what they changed it to is we have this concept now of a transaction file group, where we add these files to a group, and a transaction proceeds with all these files in mind, not just putting dirty pages on a per file basis. And then when we want to commit this transaction file group, we just commit the dirty data pages, inode pages, and then something called a master commit block. Now, the concept of this multi-file transaction thing is quite simple, but it's non-trivial to support it at the file system level, as we'll look at, or at least in f2fs, as we can look at now. So of course, it's useful if we can provide these multi-file transactions, but the data is going to reside in memory, which goes back to the problem we mentioned before. Just using too much memory for the transactions and things, canceling or aborting and stuff like that. So it would be useful if we had a way when transactions are in progress that we can swap pages to disk without affecting the transaction guarantees. So for that, they introduced this concept called stealing. And you can sort of think of it like page reclamation in the kernel, where we just swap pages out to disk until we need them later. And what it does is it allows us to swap pages from a transaction that's in progress or uncommitted to disk, reducing the memory of the transaction. So if we have a transaction that spans a lot of files and needs a lot of memory, it's useful to swap pages to disk, so we don't run out of memory. But it introduces a few issues, just the concept of stealing. And the first is that we don't want old blocks to be overwritten if we evict a page to the disk, because when we evict a page to the disk, we're writing it in a new location, we're not overwriting. And we don't want the mappings of the new pages to be prematurely checkpointed, because if we prematurely checkpoint an evicted mapping and the system crashes, then we will reload. We will reload the evicted page, and we don't want that. We want to load the old page. And we need to know when a page belongs to an aborted transaction as well. So if we want to steal pages from memory or swap pages from memory to disk, the first problem we run into is this sort of early invalidation problem. So we have a transaction here where in memory, we modify A and we modify it to A prime. And later, let's say we want to swap A prime to the disk because we're running out of memory. So we can swap A prime to the disk, but if we just think about F2FS, which exF2FS is based on, what will happen is that the old page for A will be invalidated immediately. Now at this stage, the transaction is still running. So what can happen is if we evict A prime to the disk, this is the new version of A prime, then the old version could be overwritten by some new data. And then when we abort the transaction, now instead of the old version of A being in the original location, we have this new data B, which is incorrect. So to help with this problem, they introduced this thing called delayed invalidation. And we have the same situation as before, but when we get A prime to the disk, we maintain both versions. So we have the old version of A and we have A prime. And later we could either commit the transaction or abort it. So when we commit, then we invalidate the old disk location, or when we abort the transaction, we just invalidate the new location. So quite straightforward. The second issue is what can happen if we prematurely checkpoint. So we have the same situation as before, but we're showing the file map now. So A is mapped to logical block 1 and in memory, and then at the bottom we have the disk. And at the bottom here we have the LBA, so we have 1 and 2, and A is in 1 right now. So let's say we want to evict A prime, and we write it to this new location, LBA2, and in memory we update this file map, so now A points to LBA2. What can happen is if the file system checkpoints automatically, on the disk we will have the file map for A pointing to LBA2. Now this transaction is still ongoing at this point. So let's say the system crashes. When we recover, we will load the new file map and it'll be A LBA2, not the original version of A. So we'll get A prime, which we don't want because the transaction failed. We want the old version of A. So we're breaking the atomicity there. And just to help with this problem, they introduced what they call node page pinning. It's quite straightforward again. We have A being updated to A prime, but when we evict A prime to the disk, we pin the file map for A in memory, and we don't let it go to the disk until the transaction is finished. So same situation as before, when we checkpoint, because A2, the file map is pinned to memory, because we evicted A prime, we don't checkpoint it to the disk. We just wait. So if the system crashes before we commit, later during recovery, we will just load A1, the old version, which is correct. Now, the third thing they introduced is this concept called shadow garbage collection. So at least in F2FS, if we have a running transaction, which, just to remind, is just atomic writes, we don't have the full guarantees. Garbage collection might target a block that's inside that transaction to rewrite it. And according to the paper, if this happens in F2FS, the transaction will just be aborted. So how can we do that without affecting the transaction? And there's kind of one important problem that this introduces. So what can happen is if we have a running transaction and garbage collection chooses a block to rewrite, what can happen is we rewrite the block to a new location and then there's a file system checkpoint. So this block's new location is going to be recorded in metadata. Now, when the transaction aborts, because the system checkpointed, this newly rewritten block was made durable before the transaction finished. So when we abort the transaction, we have the wrong version of the block. So to fix this problem, they introduced this thing called a shadow page cache. And this file system is in kernel space. So the page cache here refers to the kernel. So the way it works originally in exF2FS is we have this victim segment, which is a collection of pages. And we have the pointer to this value A in the page cache. And because there can only be one entry in the page cache per page, if we choose this victim segment and we have A inside it, exF2FS will recognize that A is already in the page cache. But what if A has been updated by a transaction? Then it will prematurely, persist the new version of A, not the old version, to the new segment, which we don't want because the transaction is still ongoing, hasn't been committed yet. So what they do is they introduce this thing called a shadow page cache. So the same as the previous situation, but let's say A has been updated by a transaction in the page cache and we have A prime. What happens is we can choose a victim segment and we see A, and then we check if A has been updated in a transaction. And because it's been updated in a transaction, we don't put it, we put it in this shadow page cache to get a copy of it. And then we rewrite it to the new location to finish the garbage collection. So we've just ignored this already updated value of A, and we're just rewriting the old value. So just as a more detailed example, on the left here, we have the transaction, again, just updating A to A prime. We have the page cache, this shadow page cache, and the file map. And the top is memory and the bottom is just the disk. So when garbage collection starts, we choose this first segment as the victim. And what we want to do is we want to rewrite A to a new location. But A has been updated in the page cache. So what we do is instead of putting it in the main page cache, we put it in the shadow page cache and rewrite it and update the file map. And then after we garbage collect, we update the file map and it says A4. So we have the new location of A's old value. We don't write the newly updated value of A because the transaction hasn't yet committed. If we have a system crash and we're going to load the new LBA for A, which had the old value as we wrote before. So we're not loading the modified version of A. So just to evaluate this, we can ask sort of how well do these multi-file transactions work? Do we reduce the total data written, and is our throughput increased because we can avoid, a lot of F-syncs or writing the journal files and stuff like that? So the two major applications they test, SQLite and RocksDB. And in SQLite, they express that big multi-file transaction showed beginning as one transaction. In RocksDB, they express compactions as one transaction. So a compaction can involve many, many files, and they just express that one compaction transaction instead of F-syncing all the time. So if we look at SQLite first, we take the same situation as at the start of the paper. We have 100-byte inserts, but we have 3 databases or 3 files. And on the left diagram here, so we have the LBA at the left and then the time in milliseconds at the bottom. We have exF2FS. Because no transaction support at the file system level, as we talked about before, to deal with these rollback files, which were always F-syncing location that manually. And this is what we see here. We have a ton of these different writes in the metadata data areas and different checkpoints in exF2FS. But if we look at exF2FS on the right, we only have 3 big writes because we don't need to do all these F-syncs to rollback files and stuff like that. The transactions just handled in the file system with the concepts we discussed before. So there's a lot less writing. So we say in this, at least in this example, we have 1/45 of the write volume and 1/30 of the transaction latency. because we could express this transaction just in the file system. With the throughput, we just have it on 2 disks here. And they compare it to the next slowest, at least on the right, on the left, and we have 24 times performance for ext4, and then 8 times performance on the right for ext4. But a huge gap in performance with exF2FS, which is another file system that handles transactions. So for RocksDB, if we remember, they express the compaction as one transaction, even though they involve multiple files. And then they do the YCSBA workload. So 50% reads, 50% writes, and they just record the statistics. So compared to F2FS, it's sort of almost doubles the throughput. And then compared to ext4, about 1.25 times the throughput. And if we look at the table here, we have much less F-syncs. And on the right here, we have the compaction latency in seconds. So just the time it takes for compaction. Compared to F2FS, at least, the time for these compactions is significantly reduced, because in RocksDB, the way it works right now is that we have a lot of F-syncs on the compaction path, because we don't support transaction at the file system. But because of the additions work, we can have this long-running sort of multi-file transaction without running out of memory, and without all these overheads for F-syncing and stuff like that. So if the file system itself doesn't support transactions, the application needs to do it themselves. But we can introduce a lot of overheads this way, as we saw in the first few slides. We need to handle things like rollback journal, stuff like that, which need to be synced to disk to maintain consistency a lot. So if we can support at the file system level, maybe we can have much better performance. So in this work, they introduced exF2FS, or they changes to F2FS to support these transactions. And as we just saw, we can really reduce the write application and commit times, which leads us to higher throughput and hopefully lower latencies. And some real world applications too, not just micro benchmarks. Okay, thank you.